Woo! Today I am going to solve a bonus assignment problem from my mentor. This is a really cool problem and the solution development will be really long, but it will not be boring, I'm sure. And the interesting thing is all of the functions over here are of x, y, z. So basically if f of x is ln of 1 by 1 plus x plus 1 by 1 minus x, the function over here is just f of xyz. Yeah, and the interesting thing is now the integral from 0 to 1, integral from 0 to 1, integral from 0 to 1 of f of xyz dx dy dz, this is actually equals to 1 by 2 integral from 0 to 1 ln square x f of x dx. And this property will be really helpful for us in solving this problem. Yeah, you can give a try before you look the solution, and then we can continue watching the video. Okay, so we have basically integral from 0 to 1 half and then ln square x, and f of x is ln of 1 by 1 plus x plus 1 by 1 minus x dx. Yeah, now 1 by 2 integral from 0 to 1, this is ln square x, and then this one will be ln 2 minus ln of 1 minus x square. Yeah, this is the case over here. And now after this we will have two integrals. One of them is 1 by 2 of integral from 0 to 1 ln square x ln 2 dx. Second thing is 1 by 2 integral from 0 to 1 ln square x, yeah, and then ln square x, and then ln of 1 minus x square dx. Yeah. Now let us say this as integral I and this as integral z, and we can deal with these independently. Now finding I will not be that hard. So I is just ln 2 times integral from 0 to 1 of ln square x dx. Yeah, for this we can just use integration by parts. Yeah, okay, so u is ln square x and v is just 1, so that will give us x over here minus integral of 2 ln x times 1 by x, and integral of 1 is x dx. Yeah, this is from 0 to 1 and this is also from 0 to 1. Okay, and now this will be ln 2. Now at 1 ln square 1 will just be 0, and 0 times 1 is 0, and at 0 also this will be 0. For that we will need to take limits. Yeah, we cannot directly place the values, so limit x tends to 0 for ln square x times x. Basically what we can do is we can use L'Hopital's rule if we take it to infinity by infinity form. So in this form, this is infinity by infinity form, so we can use L'Hopital's rule. We can differentiate. We have 2 ln x times 1 by x. Denominator we have minus 1 by x square. So this will be if we take this x over here, we will have 2 ln x by minus 1 by x. Yeah, now it's again infinity by infinity form, so differentiate. So we have 2 times 1 by x by, this will be 1 by x square. Yeah, now this will be 2x. Yeah, this will be 2x, and now x tends to 0, so that will be 2 times 0, that's 0. So you see why this expression is 0. Now at 1 this is 0, and at 0 also this is 0. Yeah, fine. And then should not give me let me not give big bracket, let me just give me a small bracket, and then minus this over here, the x cancels out, and we have 2, and the integral of ln x is just x ln x minus x. So we can do it by integration by parts again, and this is from 0 to 1. Yeah, this will be here. Let me give curly bracket, not big bracket, and this is from 0 to 1. Yeah, so we have ln 2, and this is minus 2 times, we will have 1, it wants this is 0, and then minus 1. Yeah, and at 0 we can again take the limit. Yeah, this is just 0 minus 0. Okay, fine. Now that is ln 2 times, this is minus 1. Minus 1 into minus 2 is 2. So we have 2 ln 2. So we have I as 2 ln 2. Yeah, and let me check if this is correct or not. Okay, so I is just, yeah, okay, fine, that is fine. I is 2 ln 2, and if I just half it, I will have ln 2. Now I part is done, and I was not that hard to be like real, but J part might be somehow difficult, because here was ln square x and here are 2 ln's. But yeah, but let's do it. Yeah, so our J is integral from 0 to 1 of ln square x ln of 1 minus x square dx. Yeah, now up to this, what we can do is, we know the series expansion for ln 1 minus x square. Yeah, series expansion for ln of 1 minus x is just minus sum from n equals to 1 to infinity x to the power n by n. Yeah, let me confirm. Yeah, this is series expansion for 1 minus x. Similarly, for 1 minus x square, we will have a similar series expansion, ln square x. Then we have sum from n equals to 1 to infinity, and a negative sign over here, now negative 1, and then we will have x to the power 2n by n dx. Now we can interchange the sum and integral. Minus 1 times sum from n equals to 1 to infinity, infinity, the integral from, and then 1 by n can be taken out. Yeah, in fact I can write this minus 1 over here as well if I want to, and then we will have x to the power 2n ln square x dx. Now this is just a modification of gamma function. Yeah, basically in gamma function, if we have integral from 0 to 1 of ln x to the power n x to the power m dx, in that case our integral will just be equals to minus 1 to the power n gamma of n plus 1 by m plus 1 to the power n plus 1. Now we can use that, and that will give us and that will give us sum from n equals to 1 to infinity. Here we have minus 1 to the power n, and the result from this is minus 1 to the power 2 gamma of 3 by 2n plus 1 to the power 3. Now minus 1 square is just 1, and this is actually equals to n equals to 1 to infinity. We have minus 2 outside the sum, and then 1 by n times 2n plus 1 cube. Now we can use partial fractions to evaluate this, and I have already done the partial fractions, and I hope all of you will be able to do that, because doing partial fractions is not that hard. Yeah, and but what it takes time. Yeah, that's why I'm doing it directly right now. Minus 2 times sum from n equals to 1 to infinity, and that will be 1 by n, and then plus minus 2 by 2n plus 1, and then 1 by n, 2n plus 1, 2n plus 1 by 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 2n plus 1, 2n plus 1 and then plus minus 2 by 2n plus 1 whole square, and again there's minus 2, is it? Yeah, plus minus 2 by 2n plus 1 whole cube. Yeah, now these two values will not we can find that. Yeah, basically we can find these values from n equals to 1 to infinity, 1 by 2n plus 1 to the power s. So this one will just be equals to Riemann zeta of s. Yeah, and then 1 minus 1 by 2 to the power s. We can use the formula to find these two values. Yeah, and for this one we can go into diagonal function. Okay, let's see how we solve this. Okay, so basically let us write this as minus 2 times, and then the sum n equals to 1 to infinity, 1 by n minus 1 by this will be dividing by 2, we will have n plus 1 by 2 in other sums. Sum from n equals to 1 to infinity, yeah, minus 2 by 2n plus 1 whole square plus minus 2 by 2n plus 1 whole cube. Yeah, now this one if you know the definition of diagonal function, the diagram of 1 plus n is just minus Euler-Maclaurin constant plus sum from n equals to 1. Okay, let me write it over here, x. Yeah, n equals to 1 to infinity, 1 by n minus 1 by n plus x. This is the definition of diagonal function. Yeah, if we use this, our sum over here, well, it looks like that sum of 1 by n is just infinity and doesn't really converge, but when there are these two terms, this will converge, and the value will be digamma of we will just have digamma of, since x is 1 by 2 over here, digamma of 3 by 2 will be there, digamma of 3 by 2, and then plus Euler-Maclaurin constant plus. Now this is minus 2 times Riemann zeta of 2, and then 1 minus 1 by 2 square. Yeah, am I correct? Yeah, and then the other one is minus 2 times Riemann zeta of 3, 1 minus 1 by 2 cube. Okay, now after this we will have minus 2. Now this will just be 1 by 1 by 2 plus digamma of 1 by 2. Yeah, but we know digamma of 1 by 2, the value of digamma 1 by 2. If you don't know, like I will attach a video over here which will explain how we find digamma of 1 by 2. Digamma of 1 by 2 will just be negative of Euler-Maclaurin constant minus 2 ln 2. Yeah, and then plus Euler-Maclaurin constant, and this over here will give us minus 2 times pi square by 6 is Riemann zeta of 2 times this is 3 by 4. Is it? Let me check if that's correct or not. Okay, that's correct. And then minus 2, and Riemann zeta of 3 is just written as like this because we don't have closed form in terms of elementary functions, and this is known as Epary's constant, and this over here is just 7 by 8. Yeah, and now after this we have minus 2 as it is, and okay, so we have minus 2 as it is. Yeah, why does it look to me like that it's the minus 2 is just unnecessary? Was that okay? It's necessary, it will cancel over there. Fine, doesn't matter. Okay, now this is 2, and these two cancel out. Yeah, 2 minus 2 ln 2, and then this will just be pi square by 4 minus pi square by 4, and then this will just be minus Riemann zeta of 3 7 by 4. Let me check if they are correct or not. Yeah, these are correct, but I do think I'm missing something. Okay, okay. But I'm missing something. Okay, so that something is here, because this sum is going from one. Because this sum is going from one, so that's why what I should do is mm, from this sum, yeah, this sum actually gives the sum from n equals to 0. Yeah, what have I written over here? From okay, so this actually gives sum from n equals to 0 to infinity. So that's why the first term will not be included in this sum, and first term will be just 1. So I have to subtract 1 actually. That was missing. And here also I have to subtract 1. Yeah, and that will like make us add two twos. Yeah, plus 2 and plus 2. So that's why we will have a plus 2 and plus 2 over here, and so this will be plus 4, and plus 4 will make a 6 over here. Okay, so this is the other part. Yeah, and now since we have the other part, we can now find the value. So okay, this is just 1 by 2 times this value, and 1 by 2 times 2 ln 2. Let us write it here. 1 by 2 times 2 ln 2 will just be ln 2. Yeah, and over here minus 1 by 2 and minus 2, that will just be 1. So let's write plus, and these two cancel each other out, and we have 6 minus 2 ln 2 minus pi square by 4 minus 7 by 4 times Riemann zeta of 3. This is the answer, and now we can just write it in elegant form. 6 minus ln 2 minus pi square by 4 minus 7 by 4 Riemann zeta of 3. This is the answer, and let me check if it's correct or not. The final check for the answer. Yeah, and the answer is 6 minus 7 by 4 Riemann zeta of 3 minus ln 2 minus pi square 4. So that's the answer, and hence we have completed the solution. Basically, the solution involved using this Newell formula, and then here integration by parts, here using series expansion and the gamma function, and now partial fractions and evaluating the sums. So this was it. Hope you enjoyed the solution. Thanks for watching. I look forward to seeing you in the upcoming videos too.